As we have understood that electrostatic potential and electric field intensity दोनों का काम क्या है, दोनों का हम यूज कर रहे हैं for describing some electric field. The difference is, as you know, electric field intensity is a vector quantity, it is in terms of force, while this potential is in terms of some scalar quantity which is the work done. Since both of them they are representing the same field, so that means there must be some relation between these two. So that is the topic we are going to discuss. We have to find out the relation between electric field intensity and electric potential. Okay. And one more thing is that electric field intensity is a vector while this potential is a scalar. So how can we relate them? You will also understand. Okay. So let us start. So to find out the relation, because both of them they are representing some electric field, let us have some charge configuration which is producing some electric field around it. So that configuration I want to keep it simplest. So I am taking a point charge which is producing some electric field around it. Okay. So in this electric field I am considering 2 points A and B, and these 2 points they are much nearer to each other, and suppose the distance between these two is dx only. Clear? So if I move a charge q from this point A to point B, so the displacement will be how much? Dx. Okay. And what about the direction of force which I have to apply? So the external force will be in the same direction. Yes. This is the direction of external force to move the charge from point A to point B. So this is the distance between these two, and it is being moved from point A to point B. And again I will consider that while I am moving this charge, I keep the acceleration to be 0. So if acceleration is 0, what does it mean? It means this external force, it must be equal to the electrostatic force, so that the net force becomes 0. And what is the direction of electrostatic force at this point? So the electrostatic force will be just in opposite direction. So to keep the acceleration 0, again we have to follow this condition that external force and this electrostatic force, they must be having equal magnitudes. So what I have done, I have chosen 2 points, point A and point B, which are at a distance dx from each other, and I am assuming that a charge q, a test charge q, it is being moved away from A to B by applying some external force, but this motion is without any acceleration. For that we have to follow this condition that external force and electrostatic force, they must have equal magnitude although they are in opposite directions. Okay. Now let us move further. What I will do, I will calculate the work done in moving the charge from A to B by 2 different methods. Once I will be using the basic formula of work done, that work done is equal to force into displacement, and another way I will be using the definition of potential difference. So let us suppose the potential at point A, it is VA, while potential at B is VB. Okay. So let us calculate the work done. Work done on Q in moving it from A to B, and this is done without acceleration. So this work done can be calculated as we know, work done is what? Force into displacement. So force I have to apply, which force I have to apply? That is the external force, and displacement is how much? That is dx only. But the known force in case of electric field, that is the electrostatic force, but electrostatic force is opposite to direction of external force. So what difference will it cause? It will cause a negative sign only. Okay. And what about magnitude of work? Magnitude of work will be same, because magnitude of both of these forces is equal. So that means same work can be calculated by using electrostatic force, but in place of external force, if you use electrostatic force, you have to place a negative sign over here. And if electric field at that point is E, because I wanted to introduce electric field intensity, if electric field at this point is E, suppose, in that case, this force can be written as QE, because we know electric field intensity is defined as force per unit charge. Hence, force can be written as what? QE. So I have used this relation over here. So from this method, I find this result, that work done in moving this test charge from point A to point B is how much? It is QE dx. I repeat this. For calculating the work done, I used the basic definition that it is the force into displacement. But work done can be easily calculated for electrostatic force. But if I use electrostatic force, I have to place a negative sign because these two forces are opposite in direction. And electrostatic force, as we know, if electric field is E, then force can be written as QE. So it gives us that work done is equal to QE dx. So this is the first way. Now, by definition of potential difference, we know the potential difference between 2 points is final potential minus initial potential. And how to calculate this? If you are calculating the potential difference, it can be written as work done in moving it from A to B upon test charge. So that is how we define potential difference. The potential difference between 2 points is nothing but the work done in moving the charge from one point to another point, like we are doing in this case. We are moving the charge from A to B, and this should be done without any acceleration. So every condition we are following there. So this work done I am writing down as dW because it is very small displacement. So that means by definition of potential difference, the work done can be written as, if I use these two terms, the work done from A to B, it can be written as Q into dV. This Q will be in multiplication with this term. Okay, so this is how we can calculate the work done using definition of potential difference. So this result is used in numericals as well, so please remember this. Work done in moving the charge from one point to another can be written as Q into potential difference between these two charges. We will discuss about this later on as well. Now let us compare equation number 1 and equation number 2. So comparing 1 and 2, we get that minus of QE dx is equals to Q dV. This Q and Q will cancel out, and from here I can write that E is equal to minus dV over dx. So this is the relation between electric field and potential difference. This term dV over dx, see, as you know, if it is dV over dt, we call it rate of change. So it is generally understood as time rate. So it is not dV over dt, it is dV over dx. So it tells us the rate of potential, the rate of change of potential with distance. So this term is known as potential gradient. Potential gradient. So this relation, the final relation, from here we have to draw two main points. The one point is the strength of field or I should say magnitude of electric field, or you can say strength of electric field intensity, that is given by this dV over dx. Means it is a potential gradient, or you can understand that it is the rate of change in potential with distance. So when you will be moving in the electric field, higher the rate of change in potential, stronger will be the electric field. So this is what this term states. What is the significance of this negative sign? Ultimately, I have to decide the direction of electric field with help of this negative sign. So we have to think in this way, that in what condition this term will become positive. When this term will become positive, that means that will be the direction of electric field. So it will be clear to you. Suppose if dx is positive, dx positive means what? We are moving away from the charge, we are moving away from the system. And suppose dv is negative, so dv negative होने का मतलब क्या हुआ? That as you are moving away from the charge configuration, then potential is decreasing. In that case, this negative sign of dv and this negative sign which is already there, that will give us the positive sign. So what does it indicate? Electric field will become positive, so that means electric field will be in that particular direction in which the potential is decreasing. Because if potential will be decreasing in a particular direction, then this dv term will be negative, and already there is a negative sign, so this negative and negative will become positive, and hence electric field should have a direction in which the potential keeps on decreasing. So that is what the significance of this negative sign, which indicates us that electric field, in fact direction of electric field should be such that potential decreases in that particular direction. So that is what the significance of this negative sign. Like in this case, you can understand this is a positive charge. So when you will be moving away from it, potential will be decreasing, because the previous topic we have seen potential was inversely proportional to distance due to point charge. So if you are moving away from it, potential will decrease. And if I ask you the direction of electric field due to this charge, that is also away from it. So that means the direction of electric field is in a direction in which potential decreases. So this is the relation we are having between electric field and potential difference. Now let us write this in component form. So in component form, suppose if you have to find out the x component of electric field, then you will differentiate the potential function with respect to x only. So this is electric field. Electric field is nothing but the derivative of potential function. So if you want to have x component of electric field, differentiate with respect to x. For y component, differentiate the function with respect to y, and for z component, differentiate with respect to z. See, I am not writing d over here, I am writing del. So there is a slight difference between these two. This type of differentiation is known as partial differentiation. So like in this case, you are differentiating with respect to x. So partial differentiation means you will treat other variables as constants. I repeat, when you are differentiating with respect to x, y and z, they will be treated as constant while differentiating. Okay. So finally, the electric field, it is having x, y and z components. If you place the values over here and you take potential function to be common, you get this expression for electric field. So this is the final relation between electric field and potential in vector form. Okay, and I have written the same relation. Electric field is minus dv over dr. This term dv over dr, it tells us about the rate of change in potential with distance. It is known as potential gradient. Okay, to make this clear, I am going to consider an example. So potential of a given charge configuration, it is something like 3x square y plus 4yz. Okay, so potential is given to us, potential function we are having, and we have to find out the x, y and z components of electric field. So for x component, we have to differentiate it with respect to x only. So it means y and z, they will be treated as constants. So let us differentiate this one. So because you are differentiating with respect to x, so y will be a constant and 3 is also a constant. So 3y को आप ऐसे छोड़ दो, and differentiation of x square with respect to x, that will be 2x. And now this term, so in this case y and z both are constant, 4 is also a constant, so this overall term is constant, so its differentiation will be 0, because we are differentiating with respect to x. So that is what the meaning of partial differentiation. And in the same way you can find out y component, which will be del v over del y. Okay, you differentiate it, x and z, they will be constants, so it will give us 3x square plus 4z. Okay, and the z component, now x and y, they are constant, so it gives us 0 plus 4y. So finally the electric field, it can be written as 6xy I cap, y component is this, so 3x square 4z j cap, and z component is this 4y k cap. So this is a general expression of electric field. If you want to find electric field at a particular point, suppose if you want to find out electric potential at a point P whose coordinates are 2, 3, -1. So now what you will be doing, in place of x you will be writing 2 only, in place of y you will be writing 3, and in place of z you will write -1, and you will get the value of electric field. Okay, so this will become so at this point electric field will become, so x is 2, y is 3, so 2 3s are 6, and 6 6 are 36 I cap. Now this term, x is 2, 2 square 4, 4 3s are 12, 12 12 12 12 minus 4 plus 8 j cap, and y is 3, so plus 12 k cap. So this will be the electric field at that point.